Recording in progress.
Great. Good morning, everyone. We have 350 people online. Good morning, Ecuador, Chile, Buenos Aires, Mexico, Brazil, good morning, Bolivia, Uruguay, Guatemala. Just so our panelists can have a general overview of what's joining Panama, Colombia. We have people from across Latin America present here today. Puerto Rico, Mendoza in Argentina, Germany. Great. Dominican Republic. Good morning. Okay. So today, and there are already 400 people online. We are happy to continue with our climate change response for health care in Latin America course. Our partners for our course, Columbia University and the Global Consortium on Climate and Health Education and BAHO. Let me remind you that we do have simultaneous interpretation available. You'll see an interpretation button at the bottom of your Zoom screen. If you click here, you can choose the language that you want to listen to, either English or Spanish. It is a 5-week course, as you might know, and today's, well, we're coming close to the end of the course. This is class number 5, and we are going to speak about data collection and surveillance. And we have 2 great panelists, dear friends, very well known by many or everyone. Dr. Rachel Lowe and Cristóbal Barcelos from the Osvaldo Cruz Foundation in Brazil. I will introduce them in short, but as you might know, we will have a 90-minute session. We will have a 60 minutes for presentation and 30 minutes for Q&A. And if you look at the bottom of your Zoom screen, you will see the Q&A session where you can submit your questions for either panelists or maybe a general question for both. And at the end of both presentations, if we have time, which I hope we do, we are going to share and discuss the questions. We will ask the panelists these questions and open the floor for Q&A. Both presentations will be in Spanish, but we do have simultaneous interpretation available in English. We will record these sessions and we will post them on our website. We will also post the presentations and the slides and the suggested readings. And ideally, I wish everyone could read these documents before the class to provide you with some background information and some of the ideas that the panelists are going to discuss. That is the link to our site. I'm sure you're familiar with it. And to introduce both our dear panelists, let me show you a very brief bio of Dr. Rachel Lowe. She is a research professor and global health resilient team leader in the Earth Science Department of the Barcelona Supercomputer Center in Spain. She is part of Tropical School of Hygiene and Tropical Medicine in London, and the Center for Climate Change and Planetary Health. She has published different papers on climate sensitive disease risk and focus on integrating Earth observations and climate forecasts in dengue early warning systems in Latin America, the Caribbean, and the Southeast Asia. And then we will hand the floor over to Dr. Cristobal Barcelos. He is a geographer, public health specialist, and a PhD in geoscience. He has worked in health secretaries in Rio de Janeiro, Brazil, and Rio Grande do Sul. And he is the coordinator of the Brazilian Climate and Health Observatory and a senior researcher at the Osvaldo Cruz Foundation. And he works with several organizations around the world on these matters. And without further ado, I want to welcome Rachel Lowe. I'm going to ask her to start sharing her screen. And thank you, Dr. Lowe, for being here. And thank you to the over 500 attendees that are joining us today. And once again, thank you all. And thank you for, Doctor, thank you for accepting our invitation for today. Hello, good morning, everyone. Thank you, Daniel, for your introduction. It is my pleasure to be here and to be part of such an important course and to share the course with my colleague, Christopher Barcelos, who will come after me. I will speak about data collection and data surveillance for climate sensitive diseases. And before starting, I want to thank everyone in my team, everyone who has participated in the studies and the work that I will present. And particularly, I want to thank Martin, who's helped me translate some of the work I will present today. So the learning objectives for today are to
first, I would like to talk about the risks of climate-sensitive diseases, especially mosquito-borne diseases, in the context of extreme weather events and also climate change. Then I will describe climate data and epidemiological data flow and the methods we apply to monitor the right climate conditions for the transmission of climate-sensitive diseases. Also, how we can transform this climate information to be used locally in early warning systems and identify hydrometeorological indicators that are useful to predict the risk of having epidemics before they actually occur. So there are in the first parts of these sessions of this course, we addressed the climate conditions that favor the appearance of dengue and malaria because of globalization processes, for instance, an increase in international trips and also global connectivity that connect areas that have epidemics such as dengue fever, and also other areas that did not have this risk before, but it's now increasing because of the mobility conditions of the populations and because of climate conditions as well. We know that temperatures are increasing in higher latitudes and also in higher elevation areas. There is also an increase in the intensity and frequency of extreme events, such as floodings and droughts, that can actually have an impact on the appearance of disease outbreaks. Nowadays, the World Health Organization estimates that half the world population is at risk of suffering mosquito-borne diseases. We published a study last year where we calculated the risk of these mosquito-borne diseases, dengue and malaria. We used several models to understand how the duration of the transmission period and the number of vulnerable population will increase in given different climate change scenarios and population scenarios as well. According to a study, if we remain the same carbon emission levels and we reach temperatures above 3.7 Celsius degrees by the end of the century, 4.7 billion people might be at risk of suffering a mosquito-borne disease. But if we take action now, we can limit this increase in global temperature to less than 1 degree. And if we did that, the number of people would almost halve. So this shows the importance of mitigating carbon emissions. Let us have now the first Zoom poll question. Which do you think is the most widely studied disease that is connected with extreme weather events? You have a minute to respond. It's malaria, cholera, diarrheal diseases, or dengue. 4 options. Okay, the one that received most votes was dengue, then malaria, diarrheal diseases, and cholera. Well, it's an interesting response because a study published last month by Tilly Alcana, a new PhD student at the Red Cross. He's part of my group in London. He reviewed the evidence that on the outbreaks of climate-sensitive diseases after extreme weather events. For instance, storms, droughts, floodings, heat waves. We found more evidence for diarrheal diseases. There are more studies documenting this type of disease. After that comes cholera, and number 3, dengue. And there were not many studies on extreme weather events and malaria. And that's very interesting for us because it guides our work as a group, and it leads us to the evidence. Our group has tried to better understand how these extreme weather events, such as droughts and floodings, can have an impact on dengue transmission. Some studies show evidence of this connection between extreme weather events and dengue, but there's a lot more to do in this field. In 2020, we published a collection of papers in BMJ, a British journal. We published a number of recommendations, strategies to strengthen the global response to climate change. And also and also to respond to the threat of infectious diseases. We address a number of strategies, and I would like to focus on 2 of them now. Increase the use of environmental and climate information in alert systems and in order to support decision making. Let us now talk about how we transform these global observations that we can access through remote sensing and satellites. And we need to see how we can transform this information to be used locally together with disease surveillance data within a co-creation process with decision makers, researchers, data managers, in order to develop alert warning systems that can actually increase resilience to climate change in the area of health. First, I would like to talk about a few indicators that we are developing within the Lancet Countdown. The Lancet Countdown is an international cooperation work that monitors the impact of climate change on health. The Lancet focuses on the impact, mitigation, economy, and also governance issues. Now I would like to discuss one of the indicators that we have been developing in order to understand how the necessary conditions for malaria transmission are changing. We combine several information layers in order to understand these favorable conditions. For instance, we are using data on temperature, humidity, precipitation levels, and we address the combination of these factors that favor transmission, and we compare it to other types of information such as elevation and type of land use. There is a very useful database for this type of study. These are the Era 5 land data. You can access them on the Copernicus platform. These are global data with several climate variables, for instance, temperature, precipitation, wind, etc., with a spatial scale of 0.1, which is approximately 9 kilometers. So this database allows us to analyze this information more accurately. And we have been using this database to understand the connection between climate and health now. It is available per hour or month since 1950 till today. You can register in the platform and you can access the data for free. Here you can download the data, choose a variable type that you'd like to study, also the data format. We use the NetCDF format, which is used, which is a grid format. And then we can use a climate data operator, also softwares, also different types of software to transform or convert that information into information that can be used by decision makers. In this case, we would like to calculate then the months that are favorable to malaria transmission and calculate for each year the number of months that enable transmission or facilitate transmission. And we want to see how this number changes over time. For the Lancet Countdown project, we have disaggregated the information according to altitude in order to understand how favorable conditions are changing in the highlands, for instance. And we also analyze the areas that have different development levels. we see then that the right conditions have increased. The highest increase has occurred in the highlands, in areas that are not fully developed. And that really guides our work regarding where we should establish early warning systems. In this study, we investigated why we see an increase in the areas that have dengue transmission. For instance, this is the first decade of this century. There were areas in Brazil without dengue outbreaks, for instance. Have a look at the south here, where the temperatures were too cold for dengue transmission, and also some areas in the Amazon with fewer people, poorer connections, poorer connectivity to the rest of the country. But have a look at the second decade. The dengue transmission area is now going further south and into the Amazon areas as well. A study published at PLOS Neglected Tropical Diseases shows a number of factors connected to this dengue area expansion, specifically urbanization and the number of months that are suitable for dengue transmission. Also, the type of connection or connectivity between cities. There are cities in the Amazon that now are connected to other areas in Brazil, which are at high risk of a dengue epidemic. How can we conduct this type of study? Brazil has very useful databases that allow us to understand the impact of climate on health. One of them is DataSource. With the database, we can access notifiable diseases. There is a collection of diseases. One of them is dengue. You can download the data from here to several spatial scales. It can be the entire country, municipalities, states, for instance. You can choose the state. You can choose countrywide. You can also choose the period. It can be every year, for instance. If you want to understand where the dengue case was notified, for instance, or where the person suffering the disease lived. This database shows the data grouped into different spatial areas. We also need to understand the population we study. We are using information from the national census. In Brazil, there is information provided by the Brazilian Institute for Geography and Statistics. Here you can see the number of inhabitants, several socio-economic indicators, and this can help us create models to understand these climate and socioeconomic indicators and their role in disease transmission. And then how can we combine the climate data in a grid format with the health data and socioeconomic data that are usually available? There are several ways to do this, to combine these data by using our packages. For instance, we use the raster package. This allows us to convert this type of data and we can combine the data with these polygons, and we can extract a summary of our variables according to population distribution in each area. Now, I would like to talk about how we can transform climate information to be used in early warning systems. Early warning systems allow us to act before things happen and also to calculate outbreak probabilities in certain areas with a few months before they actually occur. This is a type of climate seasonal forecast we develop. This is a global product as created by Met Office in the UK, but there are several other products you can use. It's always important to work with climate experts that can help us convert these data so that we can conduct the bias correction and downscaling, so that the data can actually represent the local conditions in the site. We use statistical models to learn about the associations between climate variables. And within the model, this allows us to actually say how probable an outbreak is in a given area. This is an early warning system that we developed a few years ago in Brazil in order to predict the probability of an outbreak by using epidemiological limits that are being used in the dengue bulletins in Brazil. For instance, here we used 100 and 300 people limits every 100,000 inhabitants. Also in Vietnam, we are working on an operational warning system where we can predict each month the probability of an outbreak in a month's time or in 6 months' time. One of the factors that allows us to do this is the following.
And a climate sensitive outbreak is El Nino or El Nino events. And I think that at the beginning of the course, you discussed El Nino events. Whenever there is an El Nino event, there is an increase in water temperature in the Pacific, and there is a positive correlation between El Nino temperatures and rainfall, for example, in the coastal area of Ecuador. In 2016, in the city of Machala in Ecuador, the city suffered one of the worst floods since 1998 due to El Nino event. This makes it possible to find the highest correlation between the disease transmitting vectors like dengue and the population. Together with our colleagues that work in the dengue control unit, we developed a model to predict the risk of dengue based on the meteorological station data, a station in the city of Machala, and we obtained historical data from 2001 to 2015, and together with an El Nino indicator and dengue historical data. So when it is colder and drier than usual, there is less dengue, and when it's warmer and more humid, when we have El Nino events, the dengue rates go up. So we wanted to understand the correlation, and we developed a model to understand how dengue incidence rates can be affected by climate factors, considering the annual cycle and the interannual variation that could result from other factors, for example, the segregation of serotypes or changes in the prevention measures or interventions. So the traditional surveillance practices are to calculate an endemic channel, that is the average of dengue distribution in the past 5 years, to understand when the dengue peak is expected to happen. According to 2016, according to the 2011-2015 data, we would expect dengue to peak in June. But by using our dengue prediction model together with different El Nino and climate forecasts, the model showed it would peak a few months earlier in May. After the event, we observed that really there was an outbreak, or it peaked a few months before it was initially expected, and it coincided with floods and high temperatures resulting from the 2015-2016 El Nino. So the predictability sources for our model is number one, weather forecasts. The model that we used included 24 members, and we can see that each one could predict rainfall highs in February, and the dotted line shows the observations of the meteorological station in the city of Machala. For temperature, the model showed higher temperature rates as well. This information helped us predict dengue rates at the beginning of 2016. We also used active surveillance data to correct the database for the formulation of the model. In 2016, there was a very significant chikungunya outbreak, but many of the cases that have been reported as dengue were actually chikungunya. So a serological study and surveillance data have allowed us to really improve the quality of data and prediction. One of the important aspects of this study is that by working with a climate scientist, we observed that for weather and climate forecasts, we use the grid to extract weather forecasts or predictions. And that red dot shows the location of the meteorological station in the city of Machado. Now the cross to your left shows that this is above the sea level, but now the temperatures of this grid are very much aligned with the temperatures measured in the city. And the problem is that where the grid, where the meteorological station is located, also will include part of the Andes. So the average temperature shown in this grid is actually much colder than the average temperatures observed in the city of Machala. So it is very important that when we use climate products, we really consider whether that grid represents local conditions or not when developing a model to understand the disease transmission. In a study that we conducted this year, we compared different products, Crew, Era 5 Land, Terra Climate, and World Clem. They all set different time frames and periods, and we compare them with the rainfall and temperature time series obtained in this meteorological station. So we see that crew really is much colder than the station, and era 5 shows higher rainfall rates than those observed in the meteorological station. If we now use an impact model using historical dengue data and historical malaria data in the state of Meloro in Ecuador, we can see that we get different responses and outcomes depending on the source or the product used. For malaria, we observed a positive correlation with one of the products and a negative correlation with another one. And this is very important when choosing that product for local use. We now have to, I will now explain some of the studies that we carried out to better understand and to understand more in detail the relationship between climate extremes and the risk for outbreaks. I will now open up the next poll. So what is the mosquito Aedes aegypti larvae's favorite habitat? Artificial water containers, holes in tree trunks, or pools? Rachel, it's the 30-minute mark, just a warning.
Muy bien. Todos están de acuerdo.
Great. So we all agree that artificial containers, water containers, are the preferred source or habitat for this Aedes aegypti mosquito. So dengue, chikungunya, and Zika, these are, well, humidity, rainfall, and even drought. The mosquitoes are sensitive to these factors, and water storage. So it can create a more favorable environment than a combination of drought with other factors like temperature and rainfall could lead to an increase in the risk of dengue. We published 2 papers, one in Barbados, where we found an increase in dengue rates 4 or 5 months after a drought and immediately after floods. And also we observed an increased risk 1 or 2 months after a period of high temperature. And different study in Brazil shows similar patterns, and that the impact of drought is even higher in urban areas. This is thanks, and this is results from the use of these artificial water containers. And that picture shows one of the most important favelas or slums in the city of Rio in Brazil. And the many blue dots that you can see in that picture are the water containers that the population uses for water supply when there is water scarcity and during periods of drought. So that very inadequate infrastructure and an overcrowding of the population really are very fertile grounds for dengue. That picture shows the type of temporary container that people or municipalities use for water supply. But at the same time, they turn into very fertile grounds for mosquito breeding. This model is similar to the model that we used in Ecuador, but in this case, we are using different functions to understand the delayed and non-linear effects by using, for example, draft indicators and the standardized precipitation index or the Parmetron severity index will show that a period of drought could increase the risk of dengue a few months after the drought, and combined with high temperatures will really breed ideal conditions for a dengue outbreak. We can calculate the probability of going over the epidemic threshold. This is an example for Barbados, where we went over a 75 percentile of the historic distribution to analyze the probability or the likelihood of a dengue outbreak given these factors. So in 2007, 10, and 13, the model for this period, the model calculated a higher likelihood of outbreak. And the outbreaks actually did happen during these times. In Brazil, we used the DataSUS database to analyze the relationship between dengue cases in the 2009 and 2019 period for the different micro-regions. There are around 500 micro-regions in Brazil, and together with the drought index, the Parmetron severity index, to understand the relationship between droughts that, as we can see, are increasingly intense in Brazil. And we want to understand the interaction between population living in urban areas and the increased water scarcity or the frequency of water scarcity. When we want to analyze the impact of access to water, this will have a positive correlation with the number of people living in urban areas. If we want to work at a broader scale, like microregion, this variable will not be very useful, because in urbanized microregions, there is usually good access to water, but that does not necessarily explain variations in larger cities. We've used a different database that shows the frequency of water scarcity, and that could help us detect, for example, the drought that affected Sao Paulo in 2014. There was more frequency in water scarcity events. Using this variable, we can see that in more urban areas where there was a greater frequency of water scarcity, this delayed effect was more significant in urban areas. Now, in more rural areas, like the Amazon, for example, when there were floods, the risk of dengue would increase. It is this type of information that we can combine in a warning system, especially in sites that are very sensitive to El Nino events. That picture shows a correlation between El Nino and droughts in the north on Brazil. Whenever there are El Nino events, we are going to have extreme drought events, and at the same time, we can observe floods in the southern region of the country. Now, there is also a correlation between El Nino events and temperatures. If we combine all of this climate information and the type of landscape, we could guide dengue control teams to monitor drought events, particularly in urban areas, and flood conditions, especially in more rural areas. To wrap up, let me explain some of the studies that we are conducting in Barcelona's supercomputing center. We just started on a new product for global health resilience together with other teams of the climate services and knowledge, communication, and air quality. We have organized different projects. One of them is called Harmonize, and we are working in Peru, Brazil, Colombia, Dominican Republic to develop digital technologies to create reliable databases to enhance decision-making support systems, especially in cities, islands, and mountains. I hope that I can share these findings with you next time. Thank you all.
Excelente, doctora Rachel Lowe. Fantástica presentación.
Excellent, Dr. Rachel Lowe. It was a great presentation and your Spanish is perfect. Well done. We have so many questions already at the Q&A. We're choosing a few of the questions to ask you at the end. We have almost 700 people online, so we have a great audience. Now, we would like to give the floor to Dr. Cristobal Marcelos. Can you please share your screen, Dr. Cristobal, and then we can go to your presentation. And then at the end, we'll have a round of questions and answers. Thank you. And you have the floor. Thank you, Daniel, Hilma, and everyone at Columbia University. It's a pleasure to share this presentation with Rachel, who is so close to us as a partner in Brazil regarding the analysis of data. And it's not easy, of course. The model shows us some connections which are not linear, they're not automatic. So what I wanted to share with you today, I would like to share this experience regarding the construction of the Climate and Health Observatory. We would like to stimulate the use and construction of new observatories that connect climate and health data. Today's objective is to show you the stages of entailed when building an observatory, because we need to organize the current demands in a country or a region. We need to identify the priorities we will have in the coming years regarding monitoring climate and health, and also which are the environmental, social, climate indicators that are necessary for monitoring. Also showing potential tools for visually organizing these indicators and acknowledging the role of the observatory in changing society as the one we are living in. Well, you know this already. There has been a quick evolution, an unprecedented evolution, and things have been very unequal. Now we have an estimated temperature change in the world, and nowadays we have an alarming problem in India. The map doesn't show it, but these local crises actually are interesting to us. So there is a global change. Things are not the same throughout the world. And there are major crises that can affect people's health. In Brazil, and I think that this also applies to Latin America, we listed the priorities and also the type of change, not just the temperature, but also other factors that can have a major impact on people's health. Well, the direct impact of extreme weather events, as we can see, for instance, heat waves, but not just that, also droughts, floodings, etc. As Rachel has said, also the expansion of the borne diseases. And this is related to land use, also the precipitation, the variability in precipitation, and other factors, migration as well, biodiversity loss, urban vulnerability, also water crisis. Chile and Peru are undergoing very serious water crisis right now, which affect cities, of course. Also, the effect of air pollution on health can become worse. And this is this has been a health concern, public health concern for several centuries now. But now it is getting even worse during droughts. There are several climate sensitive diseases, but they are sensitive in their own way. Rachel showed us the change in the spatial distribution of dengue in Brazil. And everything points to the fact that the disease is now moving towards the south, which used to be colder. Regarding leptospirosis, it used to appear in the northeast of Brazil, but now it has a completely new distribution. Sorry, that was schistosomiasis. And now leptospirosis now focuses on the south with higher precipitation, and also there is irrigation agriculture. Therefore, this observatory would aim to analyze a given situation, identify climate patterns and trends, and also our population's health conditions. That was number one. Number two, contribute to monitoring and warning systems, especially in emergency situations related to climate events and public health emergencies. Three, we need support for research. It's not enough to just have data or make them available. We should provide a basis for research in these climate health processes. Number four, citizen participation. The civil society must participate with information in the adaptation and mitigation policies. Well, this is the Zoom poll question I'd like to ask you. Which factors could aggravate the impact of climate change on health? One, social vulnerability. Two, biodiversity loss. Three, extreme events. Four, low response capacity in the health sector. And five, predatory use of land and natural resources. Of course, each country and region has a specific response. I think it's very important to discuss this. Well, many options. Social vulnerability seems to appear throughout our region. And then also extreme events. So, an observatory would allow us to organize and collect data so that they are available. This would be environmental data, health data, or epidemiological data. Mortality related data and socioeconomic data as well. And this has to do with vulnerability. But data are not enough. They need to be coherent with our theories and the experience we have as scientists and the population in order to create the forecasting models that Rachel mentioned. We have three types of users: managers, experts, these are the scientists, and number three, citizens. These citizens can and should include their own concerns, doubts, information and news. The observatory would have different users. Therefore, there would also be other languages that adapt. So each health issue, and that's how we began, each health issue, for instance, droughts, extreme events, water crisis, etc. I think it's a great opportunity to organize the demands of experts, the civil society, and stakeholders in order to define the problem and also determine the necessary indicators, the data sources used to obtain the information. Therefore, a website was created. This is not always the case, but I think it's very important to have a website in our current world because you can show this to everyone on the web. So of course you're welcome to visit the site. There was a major debate within the workshops how to organize the data. For instance, we get weather information from the raster. For instance, temperature, precipitation at a given day, health. On our map, for instance, dengue cases, malaria cases, and also socioeconomic factors according to municipality, with a smaller spatial unit. We convert this to municipality month, which is arbitrary, it's true, but it's also a possibility to combine these data in just one time unit and one spatial unit. This is difficult to do, but we can estimate it. These indicators allow us to compare, for instance, the data with maps, for instance, always municipality and month. So we can compare tables and graphs, etc. There are some interesting tools that are more widely available. Many times they are free. These tools are used to visualize data. There are different types of software that allow us to see the data on an organized table according to these criteria. And it allows us to convert it into an interactive map that users can use. Each health issue or problem has, for instance, water indicators. For instance, leptospirosis, which is highly correlated with floodings. So this includes metadata because experts often need to know about the source, also the quality of the data, and not just the incidence of the disease. They also need the hospitalization rates of serious cases. Also, if the laboratory has the capacity to run the diagnostic tests, what happens with the different factors and how they correlate, etc. This type of observatory then allows people to conduct searches to find data that are now spread around different agencies or services. Each agency, for instance, produces their own data, ministries of health, spatial agencies, international organizations that produce data from satellite images. And within the environment of an observatory, and this depends very much on information technology, allows us to conduct a search on malaria incidence rates, for instance, and precipitation and deforestation in a given region at a specific time. An observatory like this covers the entire country, but sometimes it is necessary to create sentinel sites. And that's happening now in Chile, Argentina, Brazil, Colombia. These countries feel the need to create these sites. In Brazil, we have a site on the border with the French Guiana, also in Manaus, which is experiencing a terrible flooding crisis because of the rising levels of the Negro River. Right now, part of the city of Manaus is underwater. Also in the semi-arid area of Brazil, the droughts, etc., etc., etc. And this is where the connection between climate and health is most studied. This is a brief example taken from one of these sites. In this area, there have been and there still are waterborne diseases and outbreaks, of course. Here, the droughts are getting worse. The region is highly seasonal. Many times it rains in the winter, but it's dry in the summer. But in the last few years, the vegetation hasn't been able to recover. And this is measured with the NDVI index, which is available in several international sources that work with satellite imaging. We can see a drop in the last few decades. Between 2012 and 2015, there was a strong drought in the region that led to a terrible diarrheal disease outbreak that killed dozens of people and caused the health system to collapse. An outbreak like this can actually be monitored using very interesting indicators. For instance, health information, mortality because of diarrheal diseases that increased sharply halfway through the year with the drought. Also, climate indicators that in our case would be the NDVI, and also the mean value. Local newspapers announced that at the time that the system had collapsed, that there was a very high incidence of diarrheal diseases among the local population. And also, they tried to interpret, to explain the outbreaks. It wasn't enough to say there is a high incidence of diarrheal diseases. They tried to determine the causes. They said that it was water contamination. According to this index, or through this index, we could actually study droughts in the region. Sorry, can you please close your presentation so that we have time for questions and answers? But we're doing well, we still have some time. Therefore, an event like this allows us to recover the disease process, the process of climate-related diseases. In Brazil, we do have information about deaths, hospitalization of serious cases, etc. But we know that these cases are caused by water contamination because natural water sources are depleted, and because the population then turns to other water sources that are contaminated. This is an example of what is our capacity to apply the necessary indicators in order to promote early warnings to predict these outbreaks, as you can see in blue within the process. And also, we should run a coherent line among events. Because of this diarrheal disease outbreak in the northeast of Brazil, we realized that an observatory should also work with the media, the press. They are a major social stakeholder, and not just the mass media, but also the social media, as we now call them, as they have very interesting information that can actually point to a local crisis. An observatory would also contribute to adaptation policies. We are working with the OPAS. Thank you, Brazil, for working with the Ministry of Health when it comes to climate change adaptation plans. And of course, there are other outputs, scientific papers, etc. This actually makes our studies coherent. And it also allows us to improve the indicators we use for monitoring. So finally, each country has a role in this data organization system. I would like to know which outputs an observatory can develop in the short term. Number one, monitoring some climate sensitive diseases. Number two, technical contributions to climate change adaptation policies. Three, develop internet sites, apps, and ICT apps. And four, write scientific papers on specific climate and health topics. So those are the four options. So monitoring. Yes, of course. Every country has its specific data availability conditions, but I think that many of them have this capacity to organize data and make them available for monitoring purposes, and of course, to encourage social participation. So some of the tasks of an observatory: understanding the relationships between climate and health, which are complex. They have several causes, they're indirect, they are long-term as well, but there are specific crises too. And this complexity should actually should not lead us to inaction. We should focus on policies that can be adopted to control and minimize the impacts. Also, we need to know which data we can access safely and permanently. We need to debate climate change, even in the midst of the pandemic. Is prioritizing climate change a luxury for rich countries, or can we do this in Latin America as well? We should also keep an open debate between the academia, governments, and the civil society. Of course, there is a language problem because each group has its own limitations, but all of them can produce and consume quality information. Thank you very much. Daniel, the floor is yours. Thanks, Cristóbal. That was excellent as usual. It's great to hear you speak, and we always learn a lot. Dr. Rachel Lowe, can you please turn on your camera and let us now address a few questions and provide some answers, because we've received many interesting questions. I'm not sure how many we can address today. We will send you some questions, and afterwards, when you provide us with the answers, we can share with them online. But let's see, we have about 10 minutes. We have some questions for Rachel Lowe. Maybe you can complement your answer as well. I think this is at the heart of everything. What happens with the reaction of some health ministries and governments regarding modeling? So first of all, we should see how accurate these are for dengue outbreaks, because for decision making, many ministries and health systems require a high certainty level in order to take action. And for predicting these outbreaks, which is the relative importance of climate regarding the deficiencies between structures, urbanization, etc., and how these infrastructure deficiencies are included in these outbreak prediction models. Thank you very much. Well, we can include in spatial and time models, we can use these mobility indicators, for instance, infrastructure, access to health services, to understand the spatial distribution. And also, if we have data, we can include the intervention level, the amount of money used in a given municipality. This type of data can be included in the model. But these models are designed to predict an outbreak probability. We use historical data to understand what is an acceptable dengue level, and also what happens in a given hospital. Weather data is a variable that is more dynamic, it changes, and it has a specific space temporal perspective. So using all this, we can decide if the conditions, are colder, warmer, drier, or if there is more rain than usual. And this allows us to see what happens every year. So we cannot predict what will happen in a given municipality, but we can say that in 3 months' time, for instance, there is an 80% probability of having more dengue cases than usual. And we need risk maps in order to decide which are the priorities, and to guide interventions. And also what happens with the balance between climate and other factors. Well, climate information actually explains variability regarding these diseases, but it is small, but it actually allows us to have a lot of information, lots of data, and we can detect changes in vector-borne disease conditions. For instance, dengue depends on population, socioeconomic conditions, also the type of serotype that is spreading, but also climate information allows us to predict all of this with a few within a few weeks' time, or a few weeks' time before things happen. Okay, this is a question addressed to Cristóbal, but of course Rachel can answer as well. Cristóbal, how important are the data collected by the citizens or the when it comes to preventing diseases such as dengue or other diseases, and how that can inform decision making at the observatory, and also decision making in general regarding citizens' science data input? Well, there is a major powerhouse stakeholder. There was one called Pedro Castellanos, and he says that health problems are determined by the community. They are not a scientific fact. Of course, scientists can actually report a drop in environmental indices and in the incidence of disease as well. And we can say that there is an outbreak, there's a crisis. It's actually the citizens and the civil society. The civil society or the population has a capacity, has a very interesting capacity to generate data, or produce data. And the development of data collection in the social media is huge. There is a project in Brazil called InfoDengue that collects data from Twitter on dengue. If many people in a specific region at a specific month start talking about dengue, then that points to a crisis, an outbreak. And what Rachel said is also important. We don't know how many cases there are, but we know there's a crisis. There is also something else that the civil society can do. They can qualify the information. If there is a dengue outbreak, which are the main and structural causes, for instance, living conditions, interrupting the water supply system, etc. And actually, the participation of the civil society is very important in this regard.
Dr. Rachel Lowe.
Another question for Rachel Lowe. Do you know examples of people of countries from the global south where the ministries of health are using these early warning systems routinely? And can you share with us some information on the topic? Well, the example I know best is Vietnam. There is a project funded by the UK Space Agency. We have worked with a group of hydrologists meteorologists, epidemiologists, and also centers that are researching dengue and controlling dengue at the Ministry of Health in Vietnam. We have developed a system similar to the studies I have presented. It's a statistical model that predicts dengue outbreaks in each province in Vietnam between 1 and 6 months before they happen. This is a system that we have developed as a platform where users can access the system each month. It's a closed system, and we can use these Met Office, UK Met Office forecasts together with the data from the current surveillance system. And we have the seasonal data. We have data from the weather system as well. This is now being used in order to guide the actions taken. In the Caribbean, we have been working with the Hydrology and Meteorology Center, also PAHO and CAFA. And in the Caribbean, and this type of system is being developed now in the Caribbean. There is currently a bulletin published every 3 months in order to include the information on weather forecasts. And of course, this provides examples about the impacts on health. This is a way to use these forecasts for health purposes. Great, thank you. Finally, Christovan, regarding the observatory. Which organization within a country should be in charge of the observatory? And can we also have subnational observatories and not just nationwide, or would we have regional observatories? For instance, we're trying to promote this idea from PAHO, actually. Can you please tell us more about this and give us some guidelines in this regard? I think that each region has its priorities. For instance, the Amazon is shared by Colombia, Brazil, Peru, and others. And for instance, Venezuela has specific priorities and climate change has different manifestations. On the Pacific coast, for instance, realities are completely different depending on the place. So the idea is to encourage a potential design of an observatory. Maybe not the climate, but we should think about, for instance, the intensity of droughts on the Pacific, the problems in the Amazon, leptospirosis, for instance, which is a major concern within the Brazil, Argentina, Uruguay, Paraguay border. And we should develop this problem in more detail, and a problem can be regional. So in a situation like this, it's always necessary to include scientists, the academia, the mass media, the civil society associations, and the government, of course. In Brazil, we started the observatory by working with the government, and this is why it's a nationwide observatory. But now this administration does not really accept climate change. They make jokes with the weather and people dying and stuff like that. Hopefully this administration will be over soon. There are many civil society organizations in Brazil that are doing this now. The Amazon has 3 NGOs now that monitor deforestation, wildfires, respiratory diseases, etc. It's another potential design from the civil society. But I think we always need the government, the society, and the academia. Great, thank you. Thank you very much to both of you. You've been amazing panelists. I think you have provided us with many specific examples, many ideas and resources in order to follow up on these debates. Today we had 700 people attending the session. We have the focal points of the Ministry of Health of almost every country in Latin America and the Caribbean. And they are responsible for climate change and health. So you're talking to the people who need to listen to you, and also to, of course, the academia, NGOs, and other civil society representatives that will help us build these models and tools in each country. Thank you very much for your contribution. I would like to invite you to attend the session next Tuesday. Can you please show this, Haley, on presentation mode, or Cecilia? I don't know who's in charge of the presentation. Well, on Tuesday, we'll be talking about climate change and mitigation, especially regarding health co-benefits. And the course is going to be over on in a week's time. It's a final session. We have almost 3,000 participants, Rachel and Christopher participating. So it's an amazing audience we have. Thank you very much for being so nice to participate with us today. And thank you for sharing your knowledge and ideas, which always inspire us to keep working. Thank you very much. And I hope you have a great day ahead of you. Thank you. Thank you very much.
Gracias a ustedes por el debate muy interesante.
Thank you for this interesting debate.